Hi class, I'm Professor Saraba and I will be reviewing the z-test today. Before we can evaluate the z-test, some conditions must be met. The first condition is that it has to be a normal distribution, and the second is the standard deviation and the mean must be given. If these conditions are met, then we can proceed with our problem. The equation for the problem is z equals x bar minus mu divided by standard deviation. The mu symbol is going to be given in the problem, so as well as the standard deviation. Well, the x bar varies. It's either given in the equation or you must add up all the numbers that are given, divided by the total. When you find the answer to z, let's open up the statistics book to the first page where it says table A. Number from the left side of the table. Once you have the z-score, you have the probability of the left side of the graph. Okay, let's try an example. A person scored a 70 on a test with a mean of 50 and a standard deviation of 10. Convert the test scores to z-scores. So our formula says z equals x bar minus mu divided by standard deviation. 70s are x bar and 50s are mu, and standard deviation is 10, which equals to 2. So our z-score equals to 2, which means that the original score was 2 standard deviations above the mean. Note that the z-distribution will only be a normal distribution if the original distribution x is normal. Okay, so does anyone have any questions?
I do. Is the z-test only used for this type of circumstance?
No, the z-test can be used for normal distribution, sample distribution, significance level, and critical level.
Okay, I got it.
Okay then, would you mind putting an example on the board for a sample distribution?
Example 9.7 on page 507. And I know that z equals p hat minus the mean of p divided by the standard deviation of the population divided by the square root of the sample population. Okay, I'll do example 9.7 on page 507. So we want to find the probability that p hat falls between 0.33 and 0.37. So I know that the equation is z equals p hat minus mean of p divided by standard deviation of the sample proportion. So we found the standard deviation for the SRS in the calculator, and we know that the population is 1,500 for the sample, and the mean of p hat was given, which is 0.35. And we want to find the probability that p hat lies between 0.33 and 0.37. Okay, so if we plug in to the equation the first number, which is 0.33, we get the answer negative 1.63 for the z. Okay, and if we plug in the second number, we get positive 1.63. Okay, so now we're looking for the probability that z lies between negative 1.63 and positive 1.63. So we have to look up the z's in table A. Okay, so referring to table A, we found that when z equals 1.63, its z-score is 0.9484. And when z equals negative 1.63, its z-score is 0.0516. Okay, so this displays the probability of the areas under a standard normal curve. And what you do to find this probability is you do 0.9484, which we got from z equals 1.63, minus 0.0516, which we got from negative 1.63, and that equals 0.8968. So we see that almost 90% of all samples will give a result within 2 percentage points of the truth about the population. Do it again.
Okay, great. Thank you, Celine. Does anyone have any more questions?
Okay, so I think I know how to do the significance level. Can you correct me if I'm wrong?
Okay, I will be doing example 10.14 on page 575.
From the information given, we know that n, which is the population, is 840, x bar, which is the SRS mean, is 272, and the standard deviation of the population is 60. The null hypothesis states that the mean of the population equals 275. That means that the mean score of all young Americans is at the checkbook balancing level. The alternative hypothesis states that the mean of the population is below 275. This is stating that the mean score of all young Americans is below the checkbook balancing level. The conditions are met because the problem states that it is an SRS, and since the population equals 840, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal. Given the formula, we can carry on with the inference procedure. By plugging in the variables, we can find that 272 minus 275 divided by 60 divided by the square root of 840 equals negative 1.45. According to Table A, we can find that the z-score equals 0.0735.
Good job, Laura. Now I'm going to go over critical level. If you look in your book on table C, it says the t-distribution critical values. And the way you find your confidence level is down underneath because they're all listed in percentages. So for an example, a 95% confidence level will equal 1.960. And you plug that into an equation desiring it. For an example, margin of error. Thank you for watching.